Okay, so today is Friday, September 2nd. We're still meeting in class, and this is ECE641. So we haven't been driven away from the classroom yet. So, and we're going to be covering our third lecture on probability, where we start getting into the issues of estimation. And I'm going to talk about Bayesian and Frequentist estimation. There's a particular problem, 2 points. I already lost my place. What was it, 2.7? Okay, 2.7. Okay, do you know what page that's on? I just saw it. Hold on. Yeah, 2.7. Remember 33, okay? So let me, before I do that though, I want to give a little context, okay? So, first of all, I want to do this. Laptop. Okay. One thing I want to point out, because apparently there might have been a little confusion about this, I apologize, it was my fault, that if you go to the web page, when I say the notes, I mean, and this is on, right? Yes. Yeah. When I say the notes, it's recording, correct? Yeah, when I say the notes, I really mean this draft textbook, okay? That's been in process forever. And so this is what I'm really going, and we're really following this, okay? Almost linearly. We'll be skipping some things because we can't cover everything. But so I'm bringing up this PDF. That's what I'm bringing up. I just downloaded that PDF. So that's good. And then, we went through most of this. Okay. One thing I wanted to do, this is a cute little thing here. This formula. So it turns out that you can, so this is an interesting thing. This is an interesting formula. So what ends up happening, and at the end of the last lecture, I talked about this, that when you're really, one of the things that you should get out of this class is just, in addition to learning the specific things I'm supposed to be teaching about computational imaging, is you should learn the general tools of working with statistics and estimation and signal processing problems. So a lot of you have had some probability, some of you have had some statistics. There's two kinds of statistics in a sense. There's the statistics that physical scientists tend to learn for analyzing data, okay? And then there's like the more probabilistic statistics, which is sometimes referred to as like inference, okay? And so we kind of use a lot of those kind of formal tools of inference in this class. Okay, so I want to teach those to you. You know, hopefully you'll learn a lot of different kinds of tools that you can use for different problems, okay? Not just computational imaging. So this falls into that same category. Multivariate Gaussian distributions are super useful on a wide range of kinds of problems. So we talked about, so X is distributed as n, say mu r, but then we're going to see, in a moment I'm going to talk about this Frequentist framework. There's two frameworks, roughly speaking, for estimation problems or for inference. One is the so-called Frequentist framework, and the other one is the Bayesian framework, okay? And as engineers, some people take it really seriously and get all hot under the collar about what is correct and what isn't correct. I'm like, whatever works, it's fine. But I would say the Bayesian framework has become more and more influential. The Frequentist framework will never go away because it serves some like core roles in solving certain kinds of problems. But the Bayesian framework has become more influential because that's really the basis of all this machine learning. It's all Bayesian inference, okay? In my opinion. I guess you could have some other kinds of interpretations for the same operations, but in my opinion, that's really what it is. So So in a frequentist viewpoint, though, the way you usually look at a problem is like, see when you flip a coin? Oh, I should have brought a coin with me because it's always good to do that. Imagine I have a coin, so I flip it. Boom. Okay, it comes up heads or tails. It's like performing an experiment. We model that as a random variable. Is the outcome of a coin flip a random variable? So, I mean, I was entrapping you, okay? So it's not your fault if you said yes. It's a very reasonable answer, okay? But the answer, at least from my point of view, is no, okay? And why? Well, because it's a physical thing, okay? Random variables are mathematical things, okay? Whereas physical, so you can model the outcome of a coin flip as a random variable, but it isn't actually a random variable itself, right? You say, well, I'm being kind of picky, but it's important to keep that concept straight because otherwise you can get pretty confused. But in any case, we're modeling the outcome of the coin flip as a random variable, right? And then the idea is that we want to learn something about the coin, so we perform the experiment many times independently. So this is sort of the basis of a lot of inference ideas, particularly in the frequentist framework, where the idea is that you perform some experiment independently many times in a row, and from that you make some inference about the nature of the world, okay? And so inevitably, in a frequentist framework, you're going to have xi. The xi is going to be, say, some fixed distribution with unknown parameters, mu, okay? So I'll put here a frequentist viewpoint. So you generate a sequence of experimental outcomes, and then xi are IID, independent identically distributed, right? For I equals 1 to P. I think that's how I do it in the notes. I think it's 1 to P. Oh no, it's 1 to N. I want to try to stay consistent with the notation so it doesn't confuse you. So, okay, fine. So now, hold on. Okay, so your observation X the observation is X, okay? And X is going to be X1, X2, Xn. So it's a matrix. The columns of the matrix are the observation vectors. They're the results of the independent experiments. Okay, and there's n columns corresponding to n experiments. Okay, so usually R here is a member of R P by P. So, and mu is a member of R P. So, you know, in statistics, they usually use the letter lowercase p to mean the dimension of your observation, and they use n to represent the number of times you perform the experiment. So they'll talk about like the small n, large p problem. That's when you have just a small number of observations of a high-dimensional outcome, right? So you measure something that's a billion dimensions 3 times, okay? And from that, you want to make some inference about the nature of the billion-dimensional thing. And you'd say, well, that's impossible, but humans do that kind of thing all the time, right? You look at one picture and you go, oh, yeah, I know what happened. Susie had a birthday party and she was happy, or something like that, you know. So, you know, you've seen a very high dimensional thing because the image is maybe represents 1 million pixels, And then from that, you immediately drew some kind of complex inference. And the reason that you can do that, by the way, is because you have a lot of prior knowledge and contextual information, right? If you were just like an alternative silicon-based life form and you saw that, maybe you wouldn't be able to interpret it, okay? So anyway, so this is your observation, X, right? And so the probability, and I'm going to unabashedly use this kind of notation, which you may find really painful, maybe, okay? That I just write X, and you have to know that X is not a scalar. I don't like to do this stuff with the arrows and the boldface and the twiddly things, because it just gets out of control, okay? Especially in this day age of tensors, you have like lots of dimensions. I just write X, and you have to know from context what it is, okay? And so the probability of X is going to be equal to the product from I equals 1 to n of the probability of the lower dimensional quantity. I don't know, I'll call it P0 because I ran it, I don't know what else to call it, xi. So it's the ith column of x, okay? Oh gosh, I really hate these things. You know, why would they, it sort of shows that they have no respect for the blackboard by the fact that they put this wheelie thing right in front of it in a way that you can't move it. Maybe you want to move over where you can see better. Okay, fine. Now the interesting thing is this. So we know how to write down the multivariate Gaussian distribution, right? But what's not so obvious, but you can show with a little bit of manipulation, is that you can write it this way for the whole matrix, okay? So this is the joint probability of all the n independent multivariate Gaussian vectors. And obviously you can write it in this simple form where you just take the product, but it's not so convenient to use this. You could also take the log, and then the product becomes a sum, but that's also not so fantastic. If you manipulate things, it turns out you can write it like this, okay? And then the key idea here is that S here is equal to the sum from I equals 1 to n of xi transpose, right? And this is what I said last time, that this is a random variable now. It's a statistic, okay? And b is equal to the sum from I equals 1 to n of xi. It turns out that the combination of the two things, S and B, are sufficient statistics for this distribution, for mu and r with this distribution, which is to say that I gave you the definition previously, but basically it's that you can express the probability distribution of x in terms of S, B, R, and mu, okay? So, and here is the form. And deriving that form, I think, is one of the homework problems, if I recall. It's not too hard to do. Mainly you need a useful identity, which is that the trace of A, B, C. First of all, everybody knows what the trace is? The trace is the sum of the diagonal elements of a symmetric matrix. Not symmetric matrix, of a square matrix. And the trace is equal to the sum of the eigenvalues, because it's easy enough to show that I'm wondering, is that always true? I feel like that's always true. That's always true, right? But it's trivially obviously true when the matrix is symmetric, but it's also true when the matrix is not symmetric, right? But it eludes me right at this moment exactly how to prove it, but I know it's true. Okay, so the trace is equal to the trace of CAB when those two expressions make sense. So if the dimensions of A, B, and C are such that you can just swap, you can just move this over here, then that's true, okay? So it turns out that because it turns out that if you take, if you take you're going to get an expression which looks like this, of xi r inverse xi, like this. So the trace of this is a scalar, right? So the trace of a scalar is just the scalar. There's no difference because it's a matrix with dimension 1, so it's sum of its diagonal elements is just it, right? So that's equal to the sum from I equals 1 to n of xi transpose r inverse xi. And that's equal to the trace of, and then the trace is also linear. So this is another step here. This is the sum from I equals 1 to n of the trace. And then, so I could take the trace of exchange the trace and the sum because they're linear. And then I can change the order and I get xi transpose R inverse, okay? And and then I can put the sum back in again. I think this is partially the answer to one of the homework problems. Because I can take R inverse out of the sum. I skipped a couple steps because R inverse is a constant, so I can take it out of the sum. Okay, and then this thing here is S, so you get the trace of S times R inverse, which is the expression you have here, right? So this is the core trick to doing that, to showing that that's true. So you should verify it, and then what you can do is you can, okay, so then this expression here is useful because it's a compact expression for the multivariate Gaussian distribution when you have IID observations, okay? Any questions about that? Was that clear? Yeah.
Could you have done that without using the trace?
Without using the what?
The trace?
Well, you know, answering a question like that is always a little tricky because it philosophically raises the question of what it means to have done it without the trace, okay? But I think roughly speaking in human terms, the answer is no, okay? Because, I mean, you could always fake something which is kind of like the trace, but you just didn't ever write the word trace down. So it's sort of like, you know, if a tree falls in the woods and there's nobody there to hear it, doesn't make any sound, kind of a thing. But the answer is basically no, you have to use the trace. In any case, it's a much more convenient way of doing it. All right? So, so that actually brings us, okay, so that's fine. Now here's the sufficient statistics, and here's another example you should work through that involves Bernoulli distribution. So the Bernoulli distribution, for each observation, x is equal to 1 or 0, okay? And the probability that it's equal to, so the probability of the sequence x, okay, so if you have, Bernoulli distributions are super intuitive, right? I mean, you just have, you're looking at how often something occurs, right? And the observations are independent. So what ends up happening is that you have xi equals 1. The probability that xi equals 1 is equal to theta, and the probability that xi equals 0 is equal to 1 minus theta, okay? And then you're asking yourself, well, if you observe a sequence, so you have x is equal to x1 through xn, okay, then the probability of that sequence, okay, is going to be theta to the n times 1 minus theta to the 1 minus to the, to the little n minus n, where n is equal to the sum from I equals 1 to n of delta of xi equals 1. So what I mean here is delta is a function which is equal to 1 when xi equals 1, and it's equal to 0 otherwise. So the n here is just counting the number of times xi is equal to 1, right? And it turns out n is a sufficient statistic for theta with this distribution, okay? No big surprises there. So, okay, if you're trying to figure out I'm trying to think of okay, so you have somebody throwing darts, okay? And presumably, okay, so you have like, you know, a random selection of people and they throw darts, okay? And then every time they either hit the bullseye or don't, right? And and you assume that the people are independent, okay? So they didn't learn anything by watching the other person throw the dart. And that they all have the same probability of hitting the bullseye. So if you want to estimate the probability of them hitting the bullseye, and you perform 100 experiments, and out of those 100 experiments, 17 of them hit the bullseye, and 83 of them, is that correct, don't hit the bullseye, right? Then given the fact that you're a normal human being and you have like a general education from grade school, what would you guess would be the probability, or not grade school, high school at least, okay? The probability that they're going to hit this bullseye. What's your estimated probability that they're going to hit the bullseye? So forget everything you've learned in this class and all the sophisticated knowledge, okay? If you like hit the bullseye, if you perform 100 experiments and they hit the bullseye 17 times out of 100, what is your estimate of the probability of them hitting the bullseye? 17 out of 100, right? It's 0.17. Wow. You didn't need to take this class to know that, right? Okay? Here's the thing. You know, I think that what happens is that we send you to school for many years so that we can teach you not to understand anything, okay? So you have to let go of all those things you don't understand anymore and just remember what you always knew, okay? Because for a lot of the problems in this class, that's the answer, okay? So now what I'm going to do is go through a very sophisticated way of showing you that the answer is 17, okay? So in a Frequentist framework, what happens is that okay, so this is the fundamental point of the Frequentist framework, which is that you assume you perform the same experiment independently n times in a row, okay? Okay, so, and then your idea is that, okay, and then so in the Frequentist, okay, you have an unknown, theta, unknown, but not random. Okay, it's not random. It's just unknown. You go, oh, that's fine, because like when you solve algebra equations, the variable may be unknown, but it's not random. Things just started getting random recently when you took this class and other classes that involve probability, right? So that's fine. And then you have a y, okay? So this is observations. And I should actually write here, y is distributed as p sub theta of little y. That's the density function, okay? I also write it as y is distributed as p of y given theta because it's too much trouble writing these little scripts, subscripts, okay? This is like more formally correct, I would say, because it emphasizes the fact that theta is not a random variable. But I write it this way too. And it also gives me the option of changing my mind and sort of putting a little sleight of hands and then making theta random without telling you, okay? Or like, you know, sort of being a little slippery on that point. So, okay, fine. So this is good, right? And then, so then the goal here is that we want to create theta hat is equal to t of y, where this is the estimator, the function is the estimator, and this is the estimate. So sometimes I'll say estimate. I noticed a few years ago that the students were getting confused about that, and I had never even noticed them being confused about it. That basically, there's the estimate, and then there's the estimator, right? The estimator is the function that produces the estimate from the data. The estimate is its value, okay? Now the estimate is a random variable. This is something that confuses people because this is a random variable. The estimate's a random variable, but the thing it's estimating is not a random variable. But that's fine. That's like what I told you last time. The mean is not a random variable. It's the expectation of something. But the average, which is the average of a bunch of random observations, is a random variable. The average is random, but the average is an estimate of the mean, okay? So this is the whole idea with the Frequentist viewpoint. And in a Frequentist viewpoint, you have bias and variance. So the estimate is going to have some bias, maybe. The bias could be 0, but it will have some bias, okay? And it'll have some variance. Now, the bias is a function of the value of the parameter. So, for example, if I have a broken clock, which Purdue was nice enough to provide us with in this. I didn't realize, by the way, that this clock was broken. I think somebody told me in the first class, because I always look at it around at 1:30 when class started, and I thought, oh, it's 10 minutes fast, but in fact, it's always wrong because it's broken, okay? But here's the thing, it's not always wrong. I lied, right? Because when is it right? It's right at 1:37 every day. At 1:37 every day, it's right, okay? So its bias at 1:37 is 0, okay? But its bias at 1:38 is 1 minute, okay? Or minus 1 minute, right? So the bias is a function of the unknown parameter. The variance of this estimator, what's the variance of that estimator of the clock's time? What is the variance? This is a tricky question, and when I say the answer, you'll go, well, yeah, obviously, okay? It's another one of those things where, well, you have to know what the word variance means, I'll give you that. But otherwise, if you just forget everything you've learned in this class, the answer will be obvious, okay? How much does that estimate vary? Huh? Well, what is the estimate? 137, right? This estimate is always 137, right? So how much does the estimate vary? It doesn't vary at all. It's always exactly the same, okay? A broken clock, the variance for a broken clock is 0, okay? The problem is the bias is really bad, okay? So the problem you have here, and now here's the problem though, with, blank, that you have a thing called, so bias is bad, right? So Frequentist said unbiased. So unbiased, they say, well, I'd like to have an unbiased random variable. Okay, here's the problem. So if we plot, the variance is the bias squared plus the variance, okay? The mean squared error, I'm sorry, is the variance plus the bias squared, okay? So if we plot the mean squared error, this would be at 137, okay? The mean square error is going to look like this. I guess over here this is a PM, and over here is 137 AM, right? It was really kind of Purdue to provide this for us, this broken clock. Okay? This is what the mean square error of that estimator is going to be. It's going to be perfect at 137 AM and PM, because I can't tell the difference. And then I don't know what exactly the point in between is, but that's going to be really bad. It's like this because you're squaring it. So it was root mean square error, it would look like a triangle, okay? So this is my artist rendition. So it looks like this, okay? So here's the problem. Is this an optimal estimator? Well, it's really hard to say it's bad because sometimes it's great, okay? But there's something very disturbing about it, right? I mean, if you told me this is a great estimator at the time, I'd be like, well, but it's broken, okay? So it's broken. So in some sense, the problem here is that, okay, fine, but it's great sometimes, but it's really bad other times. We'd like it to be at least reasonable most of the time, right? So the problem is that it's a biased estimator. So we'd like it to be unbiased. So if we put the constraint that it's unbiased, the constraint that it's unbiased is that the expected value of theta hat given theta is equal to theta. That means if we know that it's a certain time of the day, like 5 o'clock, then the expected value of the estimate should be 5 o'clock. It might be wrong, it might be a little high or low, but on average, if we measure it 20 times and average them, it should get closer and closer to the correct value. So this is an unbiased estimator, okay? Seems like a wonderful idea. It seems like, how could you argue with this? I mean, all estimators should have this property. But here's the thing. This entire class and most of machine learning is all about biased estimators, okay? So the great innovation of the last decade, certainly, have been really estimators that are biased. So even though this seems very admirable, it's not always going to be good, okay? So this is unbiased. And in some problems, there's a minimum variance unbiased estimator. You have to read this, okay, because there's a lot of issues here. There's things called, a consistent estimator is one in which if I have an infinite amount of data, so as n goes to infinity, the estimate's correct. That's not always the case, and we'll talk about inconsistent estimators. An unbiased estimator is like that. Then once in a while you get lucky and you can find a uniformly minimum variance unbiased estimator, which is to say that there's one estimator among all unbiased estimators which uniformly has the lowest variance. Why uniformly? Because the bias is a function of theta. So it could be that one unbiased estimator has lower variance at one area and another one is another, or something like that, right? But once in a while you get a situation where you're lucky, where there's only one good answer. In other words, that's like the Pareto optimal solution. It's always best in all situations. But in practical situations, it's often the case that one estimator will behave better in certain areas and another in others, okay? So it's not so simple.
To make the bias equation correct, though, for our time example, don't we need like a parameter to, like, wouldn't theta be a function of time or something like that?
Yes, that's what theta is. Theta is the time.
It's a function of time?
No, it is the time.
But your estimator would be a function of time. Because I feel like it's strange to have a single number.
So your observation would be okay. So so theta here is the time. It's the true time. Okay, and then the clock output theta hat is the clock time. I guess maybe one thing that might be a little confusing here is that what is y, right? In this particular case, you could take y and theta hat to be one and the same, okay? So, like if you're sometimes, or the other possibility is that you could have yi is the ith measurement of clock time. And then in that case, theta hat would be equal to 1 over n times the sum from I equals 1 to n of yi. It would be the average, right? Don't worry about this too much right now, because maybe I'll give some other examples. The example of the clock is nice in that it's physical and intuitive, but maybe the details are a little bit abstract or something, yeah, okay? But come back, ask me the question again if you're still confused in a little bit, okay? So that's this. So then there's a thing called the Cramer bound, which is the lower bound on the variance of it turns out that you can prove there's a theorem that tells you what the lower bound on the variance of an unbiased estimator is. So you can't always achieve that lower bound, but it's a lower bound. Sometimes it can be achieved. If you do achieve it, then you know that you can stop looking for any better unbiased estimates, because that one has the lowest minimum variance of any unbiased estimate, okay? And in that case, you say that your estimate is efficient, okay? Now, and then there's a case where there's a concept of asymptotically efficient, which is that the number of observations gets large, you converge to the Cramer bound, and it has to be properly normalized, because as n goes to infinity, if you have a consistent estimator, eventually your estimate becomes perfect. But the question is, at what rate does it become perfect? Okay, so if it becomes perfect at the appropriate rate, then it meets the Cramer bound. Okay. I'm not going to go into the details of this. If you took a statistics course, you'd learn this. But what I want to mostly cover at this point, okay, God, it always takes longer to do this stuff than I think. But I'd rather cover, well, than just blast through a lot of stuff and nobody understand it. So, is that the workhorse, you might say, in frequentist estimation is what we call the maximum likelihood estimate. And the one thing I will never forgive machine learning for, okay, machine learning has introduced a lot of useful ideas to the community, but it really bugs me that ML now means machine learning, okay? Because it used to be maximum likelihood, okay? So it's an MLE, okay, the maximum likelihood estimate. So the maximum likelihood estimate is theta hat equals, okay, so you have the probability density of, okay, this is the probability of the observations, y. Remember, y is distributed as p theta of y, okay? Y here could be, and usually is, multivariate, and then maybe independent observations of a multivariate random vector, okay? So it's not just one, it's usually a sequence of independent observations, right? That's the whole idea of IID. And then, so this is that distribution. Now, normally we'd probably Y in here, okay? But instead what we actually do is we literally put the random variable in there, okay? And that's why it's important to keep track of what's a random variable and what's not. Because in the maximum likely estimate, you literally stick the random variable in here, okay? And then you take the arg max over theta. So you take the value of theta that maximizes the probability of the observations. Seems like a very reasonable thing to do. Okay, but the way you usually do that is like this. You actually do an arg min over theta of the negative log of p theta of y. So the way this works, oh gosh, I wish I had a time dilation machine. Okay, the way this works is that L of theta is equal to minus the log of p theta of y, okay? And what I could do is also maybe put a semicolon here, and I'll put a y, okay? See? So this thing is known as the negative log likelihood. So culturally, what happens is this, that you'd say, well, this is just the log probability. The log probability and the log likelihood are two entirely different things, even though they're exactly the same, okay? Talk about a contradiction. Okay, this is the log probability when I think of it as a function of y. But when I think of it as a function of theta, it's the log likelihood. Okay, so likelihood in probability, in estimation, has a very specific formal meaning. You don't throw the word likelihood around just willy-nilly, okay? It really means something. It's the log probability, okay, as a function of the unknown parameter. It's not a probability distribution, okay, because it doesn't necessarily integrate to 1, for example. But it sort of behaves a little bit like a probability distribution. And you maximize the log likelihood. We usually deal with the negative log likelihood. And because machine learning is like a cultural tidal wave, we have to bend to the forces of machine learning. And the machine learning people sometimes do things that really tick me off, like usurping this acronym. But sometimes they do good things, like they've standardized, I think, they always talk about the negative log likelihood now. So that's kind of nice because it makes life a little easier because you don't have to worry about telling people that it's negative. Because I always like to do minimization. It's easier to do minimization than maximization, mainly because it's easier to think of ball bearings rolling downhill. To me, it's physically hard to think about a ball bearing rolling uphill, you know? It just makes my head hurt. So it's easier to do minimization, okay? So it turns out that the maximum likelihood estimate, under some simple constraints like that, the support of the distribution can't be a function of theta. I think that's the main one. Under some general constraints, it turns out that the maximum likelihood MLE is asymptotically, there's not enough time for me to spell this correctly. Asymptotically efficient. It's not unbiased. In fact, there's some classic examples of why ML estimates are biased, okay? But it's not unbiased, but it's sort of asymptotically unbiased, okay? Whatever that means, okay? Because it asymptotically reaches the Cramer bound. So it's asymptotically sort of unbiased. So the classic example of it being, so if you have yi is distributed as mu, say r, Okay, we'll make it mu r, okay? And so theta here is mu and r, okay? So then the ML estimate, it turns out to be equal to mu hat r hat, where the sufficient statistics for this distribution, we've talked about already, are b is equal to the sum from I equals 1 to n of xi, and s is equal to the sum from I equals 1 to n of xi times xi transpose, right? Correct? So the maximum likelihood estimate has to be a function of sufficient statistics. So what do you think it is?
B over N.
Yes, so this is 1 over n times b, okay? And what do you think r hat is? You got at least a 50-50 chance of giving me the right answer, probably 75, huh?
1 over N minus 1 times.
Ah, you're like a plant. You're fantastic. I really appreciate it. So this is going to be s, but you can't just make it s, right? Because you got to subtract off b squared, right? Do you know what I'm saying? So you're going to have to, so we'll have s over, okay, so yeah, it'd be s minus something like n times, okay, so the answer is that, okay, you're wrong, okay? Okay, you're wrong. And, shoot, okay. So if I did the one-dimensional case, it'd be simpler. Because your intuition, and you probably come from more of a physical science background, is that you always use the estimator mu equals 1 over n, sum from I equals 1 to n of xi. And then you take xi minus mu, say, times xi minus mu transpose, okay, sum from I equals 1 to n, and you divide by 1 over n minus 1, and that's what you call r hat, right? And that's a very good thing to do. But this is not the maximum likelihood estimate. The maximum likelihood estimate is divided by n. That's why I said there was a 50-50 chance that you'd give me the right answer, okay? So the right answer here becomes s minus, so this would be s over n minus b times b transpose over n squared, I think. Right. Excuse me? I'm sorry, say that again?
The second term?
Yeah, I could also do it with the mu hat, but I wanted to write it in terms of the actual sufficient statistics. B transpose over n squared. Because this thing here is mu hat transpose, right? Okay? So it turns out that if I divide by n, if I divide by n, that's the maximum likelihood estimate. But it turns out the maximum likelihood estimate is biased, okay? So actually, if you divide by n minus 1, it turns out that that has uniformly lower variance than the maximum likelihood estimate. So in all practical situations, one would argue there are some issues, but in all theoretically practical situations, whatever that means, it's always better to divide by n minus 1. But in this class, we'll never divide by n minus 1. And the reason is that we almost always want to use the maximum likelihood estimate because it fits into the theories better, okay? But you should work, now to prove that this is the correct answer, you have to take that expression I started the class off with, and you have to take its derivative with respect to, the way you actually solve for the maximum likelihood estimate. Let me say one last thing, and then I'll go, because we have to get out of here. Is the way you solve for it is you solve theta hat is equal to, you saw that the gradient with respect to theta of the log of p theta of y. And usually you do this for a non-random y. You find the functional form, and that for theta equals theta hat equals 0. The way and usually that gives you the answer, right? Because usually it's solving for the gradient being equal to 0. That's a necessary but not sufficient condition for the minimum, okay? But usually it's good enough, and you solve this, okay? So you should go in, that's one of the homework problems, where you have to actually derive that this is the maximum likely estimate, okay? And the derivation is somewhat complicated. We have to go right now because people are now waiting outside for us. Yeah, sorry.